Hi, my name is Bongjun Kim. Actually, yeah, thanks for having me at this great meetup. So I am a data scientist currently at 3M. I recently completed my PhD in computer science at Northwestern University. So today I'm going to talk about kind of an overview of my PhD research. The title here is how to build a machine learning model, AI model for sound recognition and less annotation effort. So before getting into the details about this talk, just briefly introducing my background. Okay. Let me. Okay, so I studied industrial engineering for bachelor degree, master's. So at the time, I've been studying probabilistic analysis of a network protocol. And then I have some work experience as a research engineer. So I was working on some R&D process management. And then I went to graduate school to study some music technology, creative coding, interactive media art. Then I moved to the US and went to this Northwestern University to study computer science. I focused on machine learning, audio signal processing, interactive intelligent user interface. And now I'm at 3M at data science. I'm working on machine learning and not only audio, also a lot of different audio signal, different sensor signals. So yeah, as you see, my background is all over the place. So I'm really curious about many things of the world. But today I'm going to focus on my graduate research that I've done during my PhD, machine learning, audio, and some interfaces. So going back to the title, so today we have three keywords: AI, sound, and annotation. So let's start with sound. Why do you care about sound? Humans, we can identify sound event. Actually, sound gives us a lot of information about our world. We perceive the world through sound, like baby crying. We can also identify different musical instrument, or we can figure out whether your car has some issues by listening to the sound. So as an AI researcher, then natural questions that comes to me is, okay, then probably AI can identify sound event as a human does. If it is possible, probably machine also can understand our world through sound as we do. So there's a area called computer auditions, the field of study. So basically they're trying to build a system that can understand auditory scenes. So if you think about how machine perceive the world through eyes, camera, then we can call it computer vision. But if we care about sound, how machine hear the world, then that's called computer audition, or people call it also machine listening field. So it actually includes different kinds of topics. So for example, audio source separation, try to extract single sources from mixture. For example, you want to extract some single musical instrument from your pop music, or you want to separate single sources from one person speaking from group of people speaking. And sound event recognition, which what I'm going to talk about today, try to identify different type of sound event. And audio scene classification is about like to identify the context or the locations where the sound was recorded. Like listening to sound, you're probably in an airport, or you are in the park or subway station, something like that. Sound localization, locating a source of sound in a space, or also music information retrieval is also a huge area. Like try to build a machine that understands music as human does and extract a lot of information from music. So, but today I'm going to focus on sound event recognition about all this area, but I'm broadly interested in all those areas. Okay, then. Why do we need such a sound recognition system? So one application would be sound-based context awareness. I just pick a couple of examples. For example, self-driving car, there should be some sound event that a self-driving car need to perceive while driving, because there's some event that they cannot capture through camera, right? there's some sound event that captured only by sound. So to understand the context. Or you probably want to analyze different type of noise sources in a city environment, because city usually has a lot of noise going on. Or home security purpose. So this is, I think, already commercialized services from Amazon Echo. So if you say, Alexa, I'm living, then actually your smart speaker start monitoring your domestic environment to detect some anomalous sound event like door knocking or fire alarm to inform you about the event. And hand washing detection, this is brand new features that Apple Watch have this year. So because of COVID, so actually monitor if you spend enough time washing your hands. So it actually detects your motion as well as the sound of water. So this is an interesting application. And also maybe this is an application in a manufacturing company. They try to detect some anomalous sound event from a lot of different kinds of machine in your factory or in your workplace. So we have a number of applications that a sound recognition system can be used. Okay, then how do we build how do we build those systems? Typical approach, assuming that we use a AI system, machine learning, there's tons of way not using a machine learning model, but in this talk, I'm going to focus on machine learning. So typical approach is to train supervised machine learning models. So supervised machine learning model actually require input and output a pair. Input is here audio event, audio signals, and output is the label. But the problem is, in audio, in order to use those supervised learning technique, you have to listen to audio and get some time-coded label for each event. For example, you have a long audio file here. Let's say you want to build some model that detect different sound event in your home environment, and you installed your microphone in your home and record 24 hours of recording, and now time to train a model. But to do that, you have to listen to the audio and do some segmentations of different sound events. And then you can feed those segmented events to the machine learning model. But this, as you can imagine, this audio annotation is really labor intensive. You have to listen to all of that and find onset, offset of such an event. So the big research question that I'm going to answer in this talk is, okay, this is an important problem, but how do we build sound recognition model with less annotation effort? So I'm going to present 3 or 4 research papers that I published over the past 2 or 3 years. I try to combine them in one theme, as an answer to these questions. So I'm going to go through each of them. The first answer to the question is this paper published last year in European Signal Processing Conference. So the first solution is weak labeling. So what is weak labeling? You have a recording here, and you have this strong label. So we call strong label, we call this weak label. Strong label means, as I said, this is going to have perfect time information. For example, there is a dog barking between 2 seconds and 4 seconds. There's a cat sound between 3 seconds, 5 seconds. So you have a full information. But again, collecting those data takes a really long time. But instead of doing that, you probably just collect a weak label like this. So for example, given 10 seconds of audio, there are dog, cat, and car sound within 10 seconds. But I don't care the onset, offset for each sound event. So obviously, collecting such information is much easier and faster than collecting a strong label. But the question is, okay, then how do we train sound recognition model using machine learning on those weak label data? Before getting into the algorithm, so the task that I'm going to use my model for is audio classification tagging problem here. So my model to be trained will take audio file, and then it output the text label like this. So it actually, a machine learning model predicts that it has, this audio file has dog barking car engine sound, not door knock sound. So this is, you can think of this as multi-class, multi-label classification problem. Okay, so then let's move to the how to train the model. So for those of you who are not familiar with audio analysis, so all the system model that I'm going to present in this talk going to use this representation as an input. So instead of just using this audio file, like 1D time series data, I actually convert this audio into this two-dimensional representations using short time Fourier transform. So this is, you can think of this as image version of audio. So it has time axis and frequency range axis on y-axis. So it actually represents the amount of energy at the certain time frame and certain time frequency bin. Let me play the audio that you can associate this sound with the spectrogram. So you probably will figure out the pattern of the sound. Let me play this. Right, there's some energy over time, there's a pattern. So all the system that I'm going to present will take this as input data. Of course, there are a lot of different ways of taking this 1D representation as input, but still, this is a kind of a typical way of doing it. Okay, now let's talk about how to train machine learning model on those wiki label data. There are a couple of existing approaches. First, we call it naive multiple instance learning. So you have this input audio. So just this is audio. Then you assume that, so you split this spectrogram, we call this spectrogram, into small time frame, and then you assume that each time frame contains dog and cat. So this is the label you have for entire spectrogram. But you assume that, okay, this time frame, every time frame contains dog cat sound. And then you compute loss between weak label and every time frame. But this is not true. Actually, it's not true that every time frame contains dog cat sound, right? But this is just one way of doing this. Slightly advanced way of doing this is, instead of assuming assuming that every time frame contains those sound event, you can actually apply some pooling operations. Like you design your machine learning model in a way that you output some cluster probability over time, like this. So for example, at time frame 2, there are 70% of this dog sound being present, right? So you have this matrices after from this your model, and you apply some pooling operation, picking some max value over time or mean value over time. Then you have this aggregate information from the matrix. Then you can compute loss between these two, and you can train the model. Another approach is slightly more advanced one. So this is exactly the same as the one that you saw before, but instead of taking mean and max, you can actually build another layer that actually learned relative importance of each time frame. So you, with having this attention layer, you can actually say, okay, for dog category, this second time frame is more important than the first time frame. So when you aggregate this information, you actually do some weighted sum over a time frame. Then you can train the model like this. So my contribution to this paper is to slightly improve this approach 3 by adding some direct supervisions to this attention layer, because as you can see, that even if it has attention layer here, how this model is trained is exactly same as approach 2, because there's single loss between your weak labeling and some aggregate information of class probability. And then you just hope that this attention layer somehow is trained correctly. But what I'm going to do is I'm going to add more supervision to this attention layer directly. So this is my model. So it consists of all the full convolutional layers. So it takes some spectrogram, and then it output at the layer 7, it actually has 2 different branches. One is the classification branch, and the other one is the attention layer. So this is exactly the same as this simplified version of this picture. The only difference between this and my model is this additional loss. I call the attention loss. So so this loss is the one we already have, but now I'm gonna add another loss, attention loss, to during the training. So what it does is it actually take the segment layer prediction from the last layer, and then it actually binarize it of the binarize the segment layer prediction so that it generates some kind of pseudo-strong label. And then you compute loss between attention matrix and then binarize the version of the segment layer prediction. So we have now 2 different losses, and then the final loss is the combination between a combination of this prediction loss and attention loss. I'm not going to go into detail about how to generate this pseudo-strong label, but the takeaway here is to binarize this segment layer predictions to make a pseudo-strong label, you have to have some threshold to binarize it. But the good thing about here is for the passive training, this threshold is adaptively changed with different training example. So this threshold changed with different training examples. So that is really good thing about this kind of like all-line binarizations. So I did simple experiment using Google Audio Set. So this is a really large audio set released by Google. It contains a lot of audio event extracted from YouTube video. So it contains each audio file has 10 seconds of audio, and it has 527 classes. It's pretty large number of classes. This is just example of the sound from the data set. This sound wave file was labeled baby crying and speech. So this is a multi-label data.
Filha, não fica triste. Ele vai tá? Vai ficar tudo bem. Vai ter a Copa de 2018.
So that was an example, one example. Okay, so this is a result. Just let's look at this table. So I compare my model with attention model without any direct supervision. So it actually got slightly improved. So that was the result. Okay, that was the end of the first paper. Then I'm going to move to the next paper. So now we have talked about weakly labeled data, and you can train model on weak labeled data and you get some prediction. But the problem is still, even if you can improve the model using some method, still there is a performance gap between the model trained on those weak label data and the model trained on strong label data, because this is obvious, right? Because strong labels has complete time information, right? So there are a lot of researchers who have been trying to improve those model on weak model. I'll call it a weak model. So after I complete this project, I was thinking that instead of like try to improve the model and like coming up with new architecture, new loss functions to improve the performance of the model trained on weak label data, probably we can come up with a new way of labeling. Because if you increase, if you have a better quality of a label, you might not need to use any complicated method because you have a better quality of input data, right? So my question is, can we just make this weak label a little bit stronger? So and not sacrifice any annotation cost. So the answer to this question is this paper. So answer is point labeling. So now we have some type of labeling we already are familiar with, so strong label and the weak label, but look at the point label. So it contains only single time point label for each sound event instances. So imagine how human annotator might annotate the sound. So listening to recording, and then let's say the human annotator found a dog barking, maybe starting 2 seconds. And then instead of finding exact onset, offset of a time event, human annotator just click any time position between this end and start time position. So maybe they can click here or they can click here. So you can click anytime, but if we do that, still it is really stronger than weak label, because even if this time information is not perfect, but it still has more information than weak label, right? But I don't think it takes that longer time than collecting point label compared to weak label, because anyways, when you collect weak label, you need to listen to the audio and you try to figure out whether this event is happening or not, right? So when you figure out, oh, okay, dog sound is happening, then you can just click any time position between this onset and offset, okay? So this point label is, I'll say, faster than strong label and better than weak labeling. Then next question is, okay, then how do we train model on this point label data? So before getting to the algorithm, so the task this time is sound event detection, slightly, I guess, slightly difficult than sound event tagging problem that I tried in previous paper. So the model takes input audio, and instead of outputting just tagging, it actually detects time information of each event. So this is the final output of sound event task. So this is, you can think of this as multi-label, multi-class classification for each time frame, not clip level. But that was the task I'm going to solve. So this is model architectures. Again, this is a fully convolutional neural network. It takes 10 seconds of audio. You can actually take any length of audio, but the reason I have this 10-second audio is this is the length of audio that I used for my experiment. And I designed this network in a way that it actually output this C by T matrix. So class probability. C is the number of classes. So if you have 10 classes in your data set, so this is going to be 10 row. And if you have, depending on your input length, the T is going to change. But if you take 10 seconds of audio, given this model architecture, it's going to be 30. Meaning each time frame cover 1/3 seconds. Okay, to train model on point label data, we need to first encode this label. So this is a point labeling maybe collected by human annotator. So we have this single line here, and then I need to encode this information to compute loss to train model. So how I encode this point label is really simple. So as you can see that we have a single time information for dog, and you just fill the 1 here, and for cat, car. This is just a really simple one-hot encoding for each time frame. So this is YP encoded point label that I would call. So now we have encoded version of point label, and we have Y hat, which is class probability for each time frame. Then we can simply compute loss between these two, right? To train your model. Class probability for each time frame, and so we can just compute a binary cross entropy between YP and Y hat to train loss. But the reality is no, you cannot do that, because point label might have really a lot of false negative labels. So this is example. Now we have a recording and we have a strong label. We don't have a strong label, but let's assume that we have a strong label. And if we had a strong label, this encoded strong label would look like this. We have a lot of 1 here for dog, right? Since we have onset offset information, that we have a lot of 1s for cat, 1s for car engine, right? But let's look at point label that we just collected. We only have a 1, 1, 1, 1, 1, right? If you look at the 0 here, these are actually false negative labels. So if you compute loss between this YP and Y hat, you're going to you will end up computing a lot of wrong, loss. So the idea here is, okay, then before just computing loss between YP, Y head, we probably need some filtering. So instead of computing cross entropy between YP, Y head, I actually filtered Y head by multiplying YP, ln Y's multiplication, and I actually have the Y head F, the kind of filtered version of it. And then I compute loss between these two. And also, since we do that, if we do this, we only use a really small portion of information because we only compute loss on this 3 time frame here. If we filter it out, then instead of using this loss function only, since I have access to weak label, because meaning that you have a point label, you also have a weak label, right? Then I can compute weak label too, weak loss too. So my final loss is combination of my point label loss and weak label loss. So this is my final loss. So here's the experiment. So this time I used urban SED dataset. So it contains 10 classes of urban noise sources, cars, horn sound, drilling sound. And I generated the point labels by selecting random time position of an event. This is important because every human annotator might pick the different time position as a point label. Someone prefer picking just a very early time of the event, or someone prefer picking in the middle. So I just randomly select the time position as a point label. And this is a result. So just let's look at this red text. So strong label, a strong model, meaning model trained or strong label. This is kind of upper bound performance in my experiment. And the model trained weakly labeled data is kind of lower bound performance. So point label is kind of the middle, right? So it actually outperformed the model on weak labeled data and slightly worse than strong model. This is good, but actually I took one more step to improve this. If you think about point label, there is some thing we can easily figure out. If you look at this, actually I told you that this model, if this model take a 10 seconds of audio, this single time frame covers 1/3 of its time, one third of seconds, 1/3 seconds. It's really short. But usually sound event longer than 1/3 seconds. Of course, they're really short sound event, like clapping. But in many cases, sound event usually longer than 1/3 second. So even if we have the single one here, they're highly likely that they're also one around this time frame. So idea is, okay, then let's copy this one to its similar neighbor segment, so that it can kind of expanding this point label, so that it can get more information. Like this, you just copy this one to neighbor segment. But the problem is, if you keep copying this one to the end, to the left, to the right, then there's no difference between this and the weak label, right? You have to stop copying at some point. Then how do we determine when to stop the copying this one? Since we can train a model on weak label data already, we use the information, kind of bootstrapping this information from the weak label data. So I measure the cosine similarity between the time frame on the segment layer predictions from weak model. I determine when to stop the copying. Here's an example. Let's say I want to copy this one to the left, to the right, and measure similarity between these two frames. If the similarity is greater than 0.5, I'll copy this one. And move to the next, copy one. Move to the next. If this similarity is less than 0.5, I stop the copy. Okay, and moving to the then I can repeat the same operations to the left too, to the right too. So now I'm done for with expanding this second class of sound, and you can repeat this for every point labeling. Then you will end up having a expanded version of point label. So this is a result. So this is really exciting. Point expanded model actually outperformed a point label. And also the F score is really close to the one trained or strong label. So take home message here is if you have to have a human annotator collect a lot of strong labels to train your machine learning model, you'll probably just need just point label, not just all the strong label. And this is just the result, the F score for class-wise, for each class. So most of the classes, point expanded model is outperformed the wig model.
Bongjun, I got a question for you on that slide.
Okay.
So how come the strongly annotated data precision went down? Is it because like there were overlaps between like, you know, like for example, dog and cat, there was an overlap? Is that why the precision is going down?
Actually, this precision is really depends on the threshold when you determine whether or not. So for example, actually the output of this network is a probability, right? Yeah. So you can say if the probability is greater than 0.5, then you say, oh, there's the sound event. Mm-hmm. If the probability is less than 0.5, there's no sound event. So that's, you can just the kind of hyperparameter you can pick. Here, okay. I picked the 0.5. Mm-hmm. And I think probably strong, if you train your model on strong label data, it will give you kind of like relatively low probability. I'm not sure what happened here, mm-hmm. but yeah, that's a good point, I think. Mm-hmm. Yeah, that's a really good point. Maybe you can look at this one too. So this is an example of model predictions. Okay, so the first row is ground truth, the truth. So we have 10 different classes of sound, and there's dog barking, starting, and car horn sound followed by car horn gunshot and street music. The second row is predicted result from my wig model. Third row is predictions from my point expanded model. If you see closely, so for example, wig model successfully predict there's a car horn sound, but wrong time location. Of course, my point expanded model also predicts the car horn wrong location, but still it has some right predictions on the right type position here. Or if you look at let's see, gunshot, it actually predict quite right at right rotation, but if you look at point expanded model, it has give you better accuracy in terms of this time information. So let's listen to this audio. Then you can look at, while looking at this figure, then you can actually listen to the audio. Yeah, that was the result. Okay. So that was the end of second paper. The next paper is slightly different topic, but so I have talked about how to build a machine learning model with less annotation effort. So the goal of this two paper is to build a machine learning model. That is your goal. But there's a situation where you might want to manually collect strong label of an event within a lengthy audio recording. So here you have a different goal. Your goal is not to train machine learning model. Your goal is just to collect strong label quickly. That's your goal. Then can we just speed up this manual strong labeling process? That was the questions that I wanted to answer. So this paper will answer the question. So again, here's a scenario. So you have a recording, you recorded some sound event in your home, and you have hours of recording, and you listen to it, and you found some interesting sound event. And then what you want to do is, okay, I want to find all the sound event that's similar to the one you just found. You want to maybe quantify this sound event throughout hours, like how many sound event it happened or when actually they happened, right? Here, again, your goal is not to train machine learning model. You just want to collect perfect time positions of a sound event. Okay, then since we have been talking about machine learning model, maybe someone might ask, okay, since we have talked about a lot of machine learning model, we can use automated system machine learning model to help you annotate this data. But the problem is, what if you want to search for new category of sound, right? So because in order to train machine learning model, you have to have your model being trained on certain type of sound event, right? But you just found some interesting sound event and you don't even know how to collect the data. You just, all you want is just to find all the event quickly. And what if you want a better accuracy? Because still, you know, machine learning has some error. So you don't want to get those errors. So you want to get like really accurate annotation information. Then let's use machine learning models slightly different way. Instead of using this automated system that I have been presented so far, we can use machine just help me to label audio. So in this picture, automated system, you train your machine learning model, maybe your machine learning model automatically label the audio by itself. That is what I've been talking about, right? But in this paper, I'm going to talk about the situation where user still want to label by himself, but still it would be really great to have some machine to help me to speed up this process. So the idea is content-based interactive searching. So machine is still fast, even if it might not be accurate. It actually can give some amount of suggestions. User can actually evaluate, and user evaluate machine suggestions as a feedback, and they are going through these iterations to achieve some goal, right? So this is system overview. So now we have a user part, system part. So this is interface actually. So interface has so user upload their audio into interface, and you have an audio file here, and then you define single target sound that you want to as your target, like initial target sound. And then system actually do some segmentations and simple feature extractions, and actually highlight some reasons that machine think that has sound event that sounds similar to what you just defined initially, right? Oh, yeah. And then user as a human annotator listen to those suggestions and then give some feedback. This is a labeling process as well as some giving some feedback, right? For example, machine gave me this suggestions. Hey, listen to those reasons. I think they have some sound event you're looking for. Then as a human annotator, listen to each of them. Okay, there's no target sound. Then you label as a negative. And it has target sound is positive. Or there's some situation where it has a target sound, but your segmentation is a bit incorrect, then actually this interface allows user to adjust the boundary of the suggestions. If you do this, and one of the interesting feature here is you listen to this gray region and you change this boundary, then actually you implicitly said that there's no target sound this gray region. So if you submit this system, it'll automatically label those reasons negative. So now in this single iteration, you got the system got this 1, 2, 3, 4 different negative labeled examples and 3 positive labeled examples. And then using this information, it actually updates some feature your machine learning model to give you another set of suggestions in next round. So you keep going through these iterations. Here's some illustrations describing how this works. So now you have a long audio recording and user select a single segment as an initial target sound. Then you submit this region to the system, and system does some segmentations and do some feature extractions and map those unlabeled example into some feature space depending on what kind of feature you use. And then suggest here, just as example, 3 reasons to be evaluated by you. and user listen to each of them and label positive, negative, and then submit this information to the system, and the system update the feature space or model in a way that pushing the negative example from the group of positive example. So we keep doing this and submitting. This is a really ideal scenario, by the way, but it actually gives you a clear picture of what's happening in the backend. Okay, so I'm going to show some
Bongjun,
demo.
question for you before.
Okay.
So that previous slide, how do you determine the duration of those windows? Is that arbitrary, or do you just get that from experience? How do you know the optimal size of that window?
That's really tricky. But for now in this system, what I did was initial segmentation length is actually the length exactly same as what the length of you select. Just assuming that probably sound event, you just select the length of that is similar to the length of the other sound in your event. And then, of course, you can change the boundary like this. So this is a user defined length of your target sound. But what system does is it actually gives you fixed length of sound, and the fixed length is determined by the size of your initial target. Yeah, I'm going to give you the example in the demo. Okay. So do you see my interface? No?
Yes, yes.
Oh, okay. Okay, this is just demo, working demo. So now we have audio file here, and let's listen to that. So this audio is contains 10 different sound events recorded in office environment. So it contains some some coughing sound, page turning.
Bonjour, est-ce que vous avez passé une bonne
human
journée?
speech. So this is kind of synthetic data. So let's say as a user, oh, this is interesting. Then you just drag this like this. And then you can move around. So my job here, my goal is I want to find all the reason within this long audio file containing sound event that sounds similar to what I just found. Okay, this is your initial target, and you clicked this button, then now it did doing some segmentation, feature extraction, and actually gave me 5 reasons. So just see this gray bar here. Yeah, these are suggestions. You can navigate this reason in this annotation track, but you can actually navigate by clicking these items. So let's listen to each of them. So it's a coughing sound that I was looking for, so you click positive. This is not coughing sound, so negative. This is laughing actually, so I will say it's negative. It has coughing, right? But I want to reduce this to get the correct annotation. It's positive. Negative. Okay, that's the end of first round. So I have got maybe 3 positive example and 3 negative example. Then you submit this system, this result to the system for next round. I just clicked it and I got a new 5 suggestions. So you keep doing this. And then you can review what you annotated so far by clicking here. Okay, so that was a kind of demo. So you just keep doing this until found enough number of trainings, enough number of sound event that you're looking for. Okay. So we just test a simple user study. We invited 20 participants who might be potential user of this kind of interface. So we compared this with annotator without any suggestions, interactions features, and just briefly, it actually to find 80% of the target sound event. Actually, using interactive one, it took only around 320 seconds, but using manual annotation, it actually took double, like 720 seconds or something. So it was good. Okay, this is my final story. We always have problem. We have another problem here. So looking at this figure, what if? So you select this initial target sound, and then let's think about initial round, the round that I just went through using my interface. But what if the first round of this, what if system didn't give me any positive example? You just have to keep annotating negative, right? It will hurt the performance. So there's some situation, maybe there are a lot of different reasons that the system didn't give me this any positive reason, but I'm just trying to mention that one particular situation where this could happen. For example, let's say this is my target sound. So you listen to it and okay, I'm interested in dog barking sound. Let's listen to this. But the problem is, as you notice, it also has some engine sound, right? But you are interested in dog barking. But if you submit the system to the annotation interface, it is extremely hard for a system to know that which sound event I'm looking for. Are you looking for dog barking? Are you looking for engines? So it will match wrong sounds. So my question was, is there any simple way as a user to tell the system, hey, I want dog barking, I don't want engine? So is there any simple interactions to solve this problem? So this is the paper to answer the questions. So I'm not going to go detail about this paper. I just briefly mentioned the main idea because I don't have enough time. So as a human, we can imitate the sound. So submitting this audio sound to the system, you can actually provide more example by imitating the sound. So you can imitate dog barking. That means, hey, in the search result, high ranked region should sound like this, and then you can provide imitation of a dog barking. And then you can also imitate car engine as a negative sound and saying high ranked region in the search result should not sound like this. So this is an example of me imitating me imitating dog barking. And this is me imitating car engine. So the expected output using this vocal imitation is something like this. So if I have a query here, initial original sound containing two different sound, dog bark, this is my target, positive target, engine, negative. And this is the potential initial result from search. And maybe the system got confused with engine and dog barking, and actually it gave you engine a higher rank than dog bark. Then if you can provide positive imitation, which is imitation of dog barking, then maybe the rank of dog barks increased higher up. And also you can add a negative imitation engine, then we hope that a dog bark is a higher rank than car engines. So to evaluate to this expected output, our system, we collected some data set. So we actually create some simple web interface where Amazon Mechanical Turk worker, they go to the interface and listen to the sound event, and we actually ask them to imitate the sound. So we gave them 302 different sound events from 455 people, that we actually collect 11,000 vocal imitations. So this is a kind of largest publicly available data set of vocal imitations. You can download this data. Actually, this is a public data. So let's listen to some example. What this image mechanical turker imitated. So this is a sound event. We actually, one of the sound events we gave them to imitate. So I just picked one example from the data set. So I'm not going to give you the result of this paper, but the story is, okay, adding this positive imitation, negative imitation actually help to improve this search result. That was the end of it. So you can actually, if you are interested in this problem, maybe you can go to my website and read the paper. So kind of wrapping up this story, so we can speed up the sound event annotation. So depending on what it is the annotated data used for, your goal is to just quantifying sound the scene, so getting accurate, strong labeling. Then you can use interactive sound event searching that I just presented, or your goal is to, okay, I want to train machine learning model on the data, and but with less annotation effort, then you can actually have some human annotator collect weak or point labeling. That was my takeaway. Do I have like 5 minutes more or something? Or it's over?
No, we're on until 8, so feel free.
Okay.
Yeah.
So this is my paper I have presented today. So you can go to my website and you can read the paper, and there's also some demo videos available, and feel free to reach out to me if you have some questions. And since I have, maybe I can introduce another project that I've worked maybe for 5 minutes. Yeah, there's some old.
Please, yes, go right ahead, please.
Yeah, so there's some old but still interesting project. There's not related to maybe what I just presented, but still interesting. Kind of old, but one of the projects I'm going to introduce is called Social EQ. So I've been working on this, really the project that I've been worked on early years of my PhD. So we were working on some audio equalizer. And let me explain what audio equalizer first. So actually it can give you a different timbre of a sound. It actually boosts or cuts some frequency, the energy at different frequencies. You can think of this as kind of filtered version, filter and image. So you have a different picture here, but if you apply some filter, you can see a different feeling of the picture, but the object doesn't change itself, but you can feel the difference. So you can apply this kind of filter in sound too. So this is original sound. Let's apply some equalizations to this original sound. Another filter. So maybe you feel how different it is. So here's the problem. Let's say you are a musician or singer and you record your singing voice, and you want to make your voice like this. Like, I want to make my voice like brighter or warmer. Then what can I do? You can use some audio equalizer looking like this. So you have a lot of knobs to control to alter timbre of your voice. But the problem is, as you can see, it's really complicated. As someone who, have no knowledge about audio processing or music productions, it's really hard to get used to such a interface. Another problem is maybe the brightness that I think is might different from brightness you think, but I have some concept in my mind, but it's hard to explain it to my audio engineer. So the goal of this project is to help those users to get those equalization curve of desired curve easily. So instead of giving them complicated interface, we can use simple system that actually ask questions to user. For example, the system contains different kinds of equalizer already, predefined equalizer setting. And then it actually give user a couple of them to ask, do you think this equalization is the concept of your bright sound? Then user actually, all user can need to do is answer those questions. Okay, like -0.3 is like, maybe it's not that close to what I was thinking, or 0.7 means, oh, pretty close. So the rating is kind of between -1 to 1. So this is really, oh, okay. Then the next question is, how many questions do I have to ask? Even if it is easy to use, if you have to go through like 20 questions, it's also painful, right? So it would be really great to just answer a couple of questions, or like 5 or 6 questions. So what I did was I tried to speed up this learning process. The goal is to reduce number of example user should rate. So to do that, we used another machine learning technique called collaborative filtering. So we deploy this web interface that people can use it. So we collect 1,500 session data from prior user, and using some active learning, we actually ended up reducing the number of questions the user need to answer from 25 to 8. So now you can actually answer, you can achieve the desired equalization curve by answering only 8 questions. So this is a video. Actually, we don't have working web demo because it's pretty old and it was built in Flash back in the day. So before shutting down, we actually recorded. Okay. Now what's happening is a user type the worm and select some sound event sources. So the goal is I want to change this piano sound warmer. That is the goal. Okay, now first example. Now you think about whether or not, how warm this sound is. Then if you think it's warm, then you put those dots to the right, very warm, right? And left, not at all warm. So you can think of this as -1 to +1 rating. So I put dot to the right. And next example. Okay, now I rated all the eight examples. Then system gave me equalization curve representing my warmness. This is the curve, the result. You can listen to it. Good thing about this interface is once you got this result, you can actually will be given single slider control the level of your warmness. So warm, not warm. Okay, that was the project that I worked on, maybe 5 years ago, 6 years ago. Another final interesting project, even older than this. So I'm really interested in generating some music using AI. So I built a simple interface generating music melody with Markov Chain. So Markov Chain is just like contains a lot of transition probability from different notes or different rhythm. So I built kind of like real-time interfaces where the musician or user can play with to generate the like some pattern of a melody followed by your rules. So that here's a video, for example. Now me as a user play some melody, set of melody. So now system recorded my melody, and I try to compute the probability or transition probability and construct a Markov chain. So I click a bunch of buttons to create it. Then now what it can do is it actually construct Markov chain. Also, it can alter the structural Markov chain in real time to provide better melody. So I can change the tempo, I define some syncopation index. So you can actually change the level of syncopations, rhythmic patterns. Yeah, that was it. Oh, just one more slide. So another project. This is not that fun, but I also worked on some audio coding analysis. Like, you know, we have different types of audio compression format, like MP3 or WAV or WMA. So the project of this is the goal is to identify which audio compression format has been used. Only looking at audio signal. So we use some frequency time frequency analysis and just looking at the audio signal without any metadata, try to predict which type of sound audio compression format was used without looking at any file extensions or metadata. This is also published in maybe yeah, it's not that old, 2018. So if you are interested in those areas, you can go to my website and read the paper. Okay, that's all for today, I think.
Awesome, awesome. Any questions and comments for Bongjun?
I got some questions. Can I ask you some questions?
Yeah, please
yeah,
go
sure.
ahead.
So in all the samples you work with, is any of them actually stereo, or is it just always a single channel?
So which one are you talking about?
Any of these sound sources you work with, right? Is any of them stereo?
I mean, just in general, any sound that I've been working on?
Right, because I actually have done some work, right? So a lot of the libraries we have out there, it just doesn't like stereo, right? It has two channels, then you know, you have to somehow just convert it to one channel.
Yeah, right. And mostly I've been working on just single channel. If there's a stereo channel, I usually combine them into one, because sometimes, because mostly about this classification. So we have to think about whether this stereo information, how much it will help for the classification task, right? So this stereo data will help to do probably some source separation or sound localization, but for classification or sound event detection, this stereo information often does not help that much compared to the mono sound. So we don't need to have we don't need to store more data. So but I think there should be some cases where the stereo audio can improve the classification result, but I don't have anything in my mind yet.
So yeah, so if you run into something that's audio, that's stereo, do you just take the two channels and take an average, or is there?
Yeah, take an average. Yeah.
Okay.
See, it seems like there would be a use case though, where at least in a real world scenario where sounds are coming from the left versus the right. You know what I
Yeah.
mean? Yeah. So you're right. Classification is classification, but I'm kind of picturing a robot, for example, or whatever, wanting to move away from or towards the sound. You probably would need to have some sort of idea of left channel, right channel.
Yeah, right. So, yeah, right. That's a good point. So it can help classification, but you know, if you have a different type of source, multiple sources in your environment, but you want to classify some sound event, as a pre-processing, you can apply some source separations. But for source separation, if you have a more special information, actually it will help. Then meaning leading to better classification results, I think. Yeah.
So in the comments, Lars is saying ShotSpotter technology sort of uses lots of channels.
Sorry, say again.
ShotSpotter. Lars, do you want to comment?
Is that like the thing that a lot of cities use to pick out when gunshots have happened in certain areas?
Oh, okay.
Ah.
I think they use that to kind of judge the distance. So like, you know, they use at least like more than 3, so they can kind of triangulate the location of the shot itself.
Yeah.
I got another question. So it seems like do you work with a lot of your sources are audio tracks you extract from YouTube. So once you build the model, have you ever taken the model outside and, you know, with a microphone and actually, you know, trying to predict what you're hearing? Let's say a car engine sound or something like that. Have you ever taken like a microphone outside and just say, okay, you know, do we detect sound, car engine sound? Or do you always work with recording?
Yeah, that's a good point. Actually, yeah, for all the paper that I published, I've only been working on those like pre-recorded audio, and I have not tested my model like grabbing my laptop or deploying those model on like Arduino or something like Raspberry Pi and take it to the. I was like, that would be really interesting. But yeah, if you really want to use such a system in real world, there should be a lot of issues. Like you have a lot of things to solve. Like you have to deal with a lot of noise, or you have to choose the right microphone, and that's whole different kind of research topic, I think. But for my research, I'm only using those pre-recorded audio actually.
Yeah, because I think one of the ideas I was thinking about is actually detecting gunshots, right?
Mm-hmm.
So you know, I collected a lot of sounds from YouTube, and for training, but then you know, the actual deployment is actually, you know, have places like schools, right, to actually record the environment. And so if I hear a gunshot going off in a school, I want to be able to alert that, right? But then my training is always YouTube videos, you know, so I kind of sometimes I wonder, okay, I train this model, how realistic it is that, you know, if I trying to deploy it to a real, you know, environment.
So one of the projects that I'm aware is that there's some project run by New York University. They actually installed a lot of the sensor signal all over the New York City. Actually, they installed it, and then still now keep collecting the data. And they actually try to build a model to detect noise, the source of noises all around the New York City. So that's a really good example. Like actually, people use their model to detect the real world data, and all the data they have is actually real recording in real environment. So yeah, that would be, maybe they have a lot of, maybe have to deal with those issues, and maybe they would probably solve some problems already.
Right.
Yeah.
Bongjun, isn't the urban sound AK? I think that comes from that same data set, doesn't it? Or is that free sound?
Right.
So it is like simulated urban sounds.
Yeah, but the single sound sources actually comes from real recording.
Mm-hmm.
Yeah, right.
Lars is asking in the comments, I wonder if there's a way to make generative adversarial networks instead of human marking sounds?
I'm not sure what. So human marking sound. Maybe
So-
you're talking about generating training data using GAN, or yeah, I think there's a research paper like so. The problem is in real recording, you really hard to get isolated sound event. Always like there's all the mixture sound. So it is hard to train a model. So one of the way that I suggest is, okay, we can mimic some sound. But yeah, there's some recent paper, I think they try to build synthetic training data using GAN. So initially they use the GAN to augment their training the image domain, but people have started applying those GAN to audio domain to augment their training data set or generating more isolated sound data. So I think that's possible, I think, but I haven't tried it yet.
Yeah, I have worked with some neural generated sound for text to speech. So that is, I think it's kind of possible, Lars. So I'm not.
Yeah. There's a lot of paper about speech generation, but what I'm talking about is people started using GAN to generate environmental sound, like natural sound, not just speech. But they just started, I think.
That it's kind of a point about those spectrograms that you were creating. Was it is it always like 10 seconds? I think you were using 10 seconds. Some of those spectrograms, are they 10 seconds? Or? Yeah,
all the data set that I use happen to be the 10-second segment. So, but the model that I present for the second paper actually takes any length of audio. It will give you a different size of output matrix though, but actually it can actually take a different length of audio. It can take 5 seconds, 4 seconds, but the data that I use are the 10 seconds long segments actually.
How many samples do you use when you are training a model like this?
How many what?
How many samples?
How many? The data set?
Yeah, the data set. Are we talking about like hundreds, thousands, tens of thousands?
For example, for the second paper, I think I have a slide. For the second paper, I used 6,000 audio file for training and validation and testing 2,000. And the first paper, actually, I used a lot more. For training, 20,000 recording, so roughly 58 hours of recording, and tested 53 hours of recording. Yeah.
Oh, all the data.
Yeah, was that all labeled? Is that what you were
All
saying?
labeled.
Yeah.
Any other questions, comments for Bongjun?
What about transfer learning with a model like this? Is it possible to adapt it for transfer learning?
Question.
Yeah, actually, I used transfer learning. I didn't mention, but for the second paper, this point labeling, actually, I didn't train from scratch because this one is a really small number of training example compared to the first one. So I start with one of the model released by Google called VGGish model. So I start with that. I import those weight to my model, and then I just fine tuned using my data.
Okay.
Yeah.
Thank you. This is very good.
Thanks.
Yeah, I was just got a quick question around the point labeling. Where has that evolved on? Is that starting to be used in practice? I know you sort of wrote this paper on it, right, and presented it. Where it seems kind of groundbreaking, I guess. What you did, has it been picked up and used as far as you know, or?
That was my last publication in my graduate school, and I graduated, and yeah, I don't know. Maybe if I had more time, maybe I could have extended the paper and actually build some interface. People can use it. Yeah, that would be really great. But I'm not sure if someone else can do that. Yeah.
I just wasn't sure if another company had picked it up or somebody tried to productize it, or, you know, I guess you never know, right? You sort of publish it and leave it out there and sort of see what happens, right?
But now research trend out there now is they try to use the unsupervised learning.
Okay.
So even without any label data. So I don't know, maybe, I'm not sure. Yeah, if people want to use those data.
Yeah. Well, it certainly seems like a huge time saver. Like you said, you don't need to choose the beginning and end stuff. And then especially, and then the unsupervised stuff, like you need a lot of data.
Yeah, this is especially for someone who actually want to build your own model. You know, a lot of people these days DIY, they just maker people, you know. They if they want to build a model just for a small project for your own recording, using your own recording, you have to go through the annotation process. And then that'll be really useful, I think.
Yeah, for sure. Yeah, that's cool.
So are you currently continuing to work with sound right now in your current?
Oh, actually, yeah. So at 3M, I'm working on more general signal processing, but at the same time also doing audio. So kind of like I expanded my expertise to other area, like more general signal processing, like other sensor data. So audio is, you can think of as sensor data, audio too. So yeah, I think I'm doing audio too.
It's just it sounds anything that's waveform, right?
Yeah.
Sure.
Good stuff.
Great. Very good.
So on behalf of our community, Bongjun, I want to say thank you so much for sharing your expertise, sharing your work with us. And suddenly I'm thinking, you know, you shared your contact information. I can see the conversation with some of the attendees here, you know, going on with you. So thank you so much for sharing your work with us. I appreciate it.
Thank you for inviting me. It was fun.
Yeah, thank you for setting this up. Very good.
Yeah.
Thank you.
Thank you.
Well, our next meetup will be the first Thursday in January, right, Eric?
So January 7th. So we were lining up the speakers. We're just in the, I want to say, stages of just confirming stuff. So as soon as we have that stuff firmed up, I will be sharing the information. And as Justin mentioned earlier, if you want to present, you know, please feel free to reach out to us. If you know somebody that is working in this field and would make for a good presenter, feel free to reach out to us. So one thing I want to add is our community fills out the entire spectrum. So we have, you know, practitioners like Bongjun, and then we have people that are new to AI and just curious and wanting to learn. So I think it's really a home for everybody. So yep. And then one last thing I wanna request is feel free to help us spread the word about this meetup, and you know, help us grow this community. Thank you. Justin, am I missing anything?
No, I don't think so. I think you hit the nail on the head. I posted a link to AppliedAI.mn. I'm assuming everybody on here knows about that, but if they don't, please go there because that will direct to our meetup page. And like Eric said, post about us on social media, you know, and let's get the word out and get more and more people involved.
Awesome.
Cool, everyone. Well, thanks again for coming tonight. Thanks again, Bongjun, for speaking, and we'll see you all next month for sure. Have a good holiday and New Year.
Yes. Yay, to a better 2021. Yeah. All right,
y'all. Thank you.
Thank you, everyone.
Thank you.
Bye-bye.
Bye.
Bye.